So now that we've developed the concept of a definite integral, we need to revisit the properties we know from indefinite integrals. The good news is they all hold, and we also have some new properties that we're able to work with. So let's look at the first one. Let's take them one by one. Obviously, this isn't very mathy, but it does say what's true. When there's no area, there's no width, obviously. So an integral or an antiderivative evaluated on an interval that starts at a and ends at a equals 0. And there's some logic to that algebraically. If you take the antiderivative of a and you subtract the antiderivative of a, that would equal 0. And visually, you're looking at a graph where all you have is height at some point a. So there's no width, no area, no integral. Next up is if we look at a interval backward, instead of going from a to b, we go from b to a of some function. Well, that equals the opposite of taking the integral in the right direction, a to b, or excuse me, in the forward direction. And again, there's some logic to this. If you look at a number line, or let's go ahead and look at a graph, and you've got a function. If I take the area on an interval from a to b, well, definitely the area is just the area. It's a positive value. But the f of a minus the f of b, because b is greater than a, it's going to lead you to a negative value. So you get the negative area. So the area, you'll have to make some sort of a mental or calculational adjustment to make the area positive, but the integral itself is negative if taken backward. So the next one comes in very handy with a lot of the calculations we'll be doing. It says if you're evaluating on some interval from a to c, that you could break this into subintervals. So this antiderivative, or this definite integral, would be equal to a to b of the same function, plus take the integral from b all the way to c of the same function. And this is also pretty intuitive. If I sketch it up real quick, say this is the interval, the area that I've calculated from a to c. If b falls someplace in between, it makes sense that the area from a to b definitely matches the area, or excuse me, the area from a to b plus the area from a to c would definitely be equal to the entire area a to c. So it just means that you can break this up. You can break it up into more pieces, or you can break it up into just two, or whatever you want to do, whatever you need to do to solve a problem you're working on. So two of our old favorites hold. If I have a constant times some function of x dx, then I can take the constant out front and evaluate the antiderivative of just the function, and that holds true when I have intervals as well, or definite integrals. Also the sum and difference rules. So if I'm finding the integral, taking the integral of some function of x plus or minus some g function of x dx, I can break these up into the f of x dx plus or minus the g of x dx. So we've worked with these a bunch. Nothing's changed now that we have intervals of integration or limits of integration. It works exactly the same way. There we go. With definite integrals as with indefinite integral. And the last two just speak to the nature of inequalities. The first one, number 5, says that if f is integratable, and by the way, if it's continuous, it's assumed to be integratable. And, oh, I left a little bit out here. If f of x is greater than or equal to 0 and integratable, then the antiderivative is going to be greater than or equal to 0. Basically, if f is a positive function, then the antiderivative is going to be positive. There's some logic to that, and there's some intuitive logic to that. If we look at a graph where the function in the first quadrant is continuously positive, it's continuous and positive, and we evaluate it on some interval a to b, then the antiderivative from a to b of that function has to also be greater than or equal to 0, just using the math that f of b, which is a positive number, minus f of a, which is a smaller positive number, that's going to be greater than or equal to 0. And last but not least, if you have a function f and it's less than a function g, then the antiderivative of f is actually going to be less than the antiderivative of g. And again, totally logical once you look at the picture. Suppose this is g, a function g, and say this is a function f. If I take the antiderivative, or the area on an interval from a to b, well, the area of f is clearly less than the area that includes g and f. So inequality is preserved. So let's write this up. On an interval a to b of f of x, dx is less than, and I guess we could say less than or equal to. No reason not to have an equal in there. If they're equal functions, then the area would be equal. The antiderivative from a to b of the g function of x dx. And that's it for the properties. Let's do a couple of examples and see if we can use them. So let's calculate the antiderivative from 0 to 0 of cosine of x. So we have a property that says this is going to equal 0, but let's go ahead and calculate it. The antiderivative of cos x is negative sine x, evaluated on the interval from 0 to 0. And so that would be negative sine of 0 minus negative sine of 0. At this stage, I don't really care what the sine of 0 is, but I do care that it's defined. So negative sine of 0, sine 0 is definitely defined equals 0, so I get negative 0 plus 0 just equals 0. So I've confirmed the first property. So another example. Let's take the antiderivative from 4 to 1 of x squared dx. So this would be this property. I could just calculate from 1 to 4 and make it negative, but let's just take it through the process. So the antiderivative of x squared is x cubed over 3, which still needs to be integrated on the interval 4 to 1. So 1 cubed over 3 minus 4 cubed is 1664 cubed. So 1 take away 64 is negative 63 thirds. So remember, in this case, only the integral is negative. If it were used as an area, and the integral has many applications, only one of which is area, the area of such a curve would, well, I actually know what that curve looks like, so I don't need a squiggle, do I? The area of such a curve would be positive 63 thirds, but the evaluation of the integral working backward is a negative 63. And last but not least, let's compare two functions. Let's take f of x equals x squared and g of x equals x. So if I graph these, and I'm only going to graph them on the first quadrant just for ease. When I integrate it, I'm going to choose an interval on the first quadrant. So x squared looks like this, and y equals x looks like this. So g of x is definitely less than, g of x is definitely greater than f of x if I choose the interval from 0 to 1. Because at 1, they're equal to each other. So let's calculate these antiderivatives. So the antiderivative from 0 to 1 of x squared equals, well, luckily we already know what that is, x cubed over 3 evaluated from 0 to 1, which is 1/3 minus 0, so it's 1/3. The integral from 0 to 1 of x, I left out my dx, didn't I? dx equals x squared over 2 from 0 to 1. So we're looking at 1/2 minus 0, so 1/2. And we can now definitively say that the antiderivative of f, so if f of x is less than g of x, the antiderivative of f of x, 1/3, is strictly less than the antiderivative of g of x, which is 1/2. And of course, visually, that makes total sense because we're saying that this area in orange is less than this area in purple, and that is clearly true when you look at the picture.